Hi everyone, welcome back to another Calculus 12 video. Today we're doing 11.2, which is the fundamental theorem of calculus. And like I said to you before, it's sort of just a summary of things we've already been learning in chapters 9 and 10. So remember, I've combined and made this one unit with chapters 9, 10, 11. So let's dive in. It says if f of x is continuous on the interval ab, and f prime of x equals f of x, then, well, this stuff in the box is what we've been doing for the last few classes. So if we take the antiderivative from a to b of f of x, we know that it's f of b, so f of the upper limit minus f of the lower limit, which is a. So again, that's just what we've been doing already. Now you know that it's a part of the fundamental theorem of calculus. Funny how things work. That makes it sound like it's a big deal. It sounds so formal. If you hear something like the fundamental theorem of calculus, it's like, oh my gosh, what is that? But you get to see it's just the same old casual stuff we've been doing, plugging things in, checking to see what they're equal to. So let's take a look at f of x equals 1/2 x. If we were to apply this, we would want to take the antiderivative of this part. So we would get, if I move the 1/2 off to the side, this is like saying x to the 1. So we would actually get 1/2 x squared. So do you see that we would then end up with 1/4 x squared for our antiderivative of this thing? So that's the first step. That's what we're working with. And then now that we know that that's the antiderivative of it, we can check if what we've done is correct. So you don't need me to mark this stuff or check for you. How we could check is by doing the opposite, because that's what they are in relation to one another. So if I have d dx of 1/4 x squared, then that would be like me saying 1/4. And then if I take the derivative of this part, it would be 2x. And then when I work my way through that, notice that the 2 and the 4 would cancel. So I end up with 1/2 x, which is my original here. So I know that I've done it right. So see what I mean about how they're sort of opposites, and we can use that in order to check to see if what we're doing is right. So then, if I want to, so therefore, that's my little symbol for therefore, if I want to check the interval from 4 to 6, let's say, so remember 6 is the upper limit, 4 is the lower limit, of 1/2 dx, so the one that we originally started with, then it's just what we found here, which was the 1/4 x squared, and then I would want that from 4 to 6 using our notation here. Kind of flying through this, but I do feel like this truly is review from what we've done the last few classes. And then in this case, if I'm doing this, I'd want to take my upper limit and plug that in. So 1/4, 6 squared. And then I would want to subtract from that the lower limit. So subtract 1/4, 4 squared. And when I work my way through and clean that all up, which you all know how to do. You can hit pause and do that if you want to find out for sure, but I know you all know how to do that. It would just give us an area of 5. And although I didn't ask for it, if I wanted to sketch this out, we would just have, let's say that's my 6, and I'm going to do that as 4. That would be telling me that this area from 4 to 6, like from the 4 and the 6 there, is equal to 5 when we work our way through what it is that we're getting. So 5 would be the area under the curve. Okay, so I think I'm going to assume you're pretty good with that. Next one, determine the displacement of a particle from time t equals 1 to t equals 4 if it has a velocity function that looks like this. So this is what we're working with. Displacement, first of all, is the area under the graph. So there's a new concept that maybe you didn't know before. So that is new and that you do need to know. So, but the rest of this, do you see what I mean? repetition of the same old pattern. We're doing the same thing as before. It's the area under, more specifically, of a velocity time graph. So if I want to sketch out what this velocity and time graph would look like, it would be something like, I'm going to say this, just to roughly sketch it out. And if that is my 1 and it goes up to, let's say, 4, like this, then it's this portion here that we're talking about or that we're interested in. Okay, so then therefore, the displacement would be from 1 to 4, so it's the colored in shaded part on the graph there, of t squared minus 2t plus 5 dt. And the rest of this is just us working our way through this. So I would take what I have here and I would find the antiderivative by thinking backwards. So I know that this portion here is going to be our 1/3 t cubed minus, if I go to here, we're going to have t squared. The 2's will cancel because we've multiplied by 1/2. And then plus 5t when I'm dealing with that last part there. And then I know that I'm looking for from 1 to 4 because of the intervals that were given to me. It says from time t equals 1 to t equals 4. That's how I know this. And so we go through the same old process. If I want the upper limit, I would take this 4 and I'd plug it in. So I'd have 1/3 4 cubed minus, just 10 minutes, Ginny, minus 4 squared plus 5 times 4. And then I would want to subtract from it the lower limit. So I'd have 1/3, and here I'd have 1 cubed minus 1 squared plus 5 times 1. So the same old process that we're usually doing. And again, I know you all know how to add and subtract things and do all this, so I'm just going to tell you the whole thing equals 21 when we work our way through that. Okay, so then this is, again, going back to some stuff you already know. If we look at these basic rules, this truly is a summary of things we've already done. If we have something like this, we're looking for the antiderivative of a to b of k f of x dx. Just remember, you can take the coefficient k and shove it off to the side and work with the antiderivative or the, I can't think of the word, the integral, the definite integral on its own off to the side, which we've practiced several times. This is just me putting it together at the end because I figured you going through it with actual numbers would make it easier for you to grasp these concepts because they look kind of crazy. So if we look at this number 2, if we're looking for a to b f of x dx, it's the same thing as negative b to a if we were to flip it. And we kind of did that when we were looking at which one is the higher one, which one is the lower one. So it's just putting this into a summary. You could do without this and you'd be fine. If we look at number 3, we have a to b f of x dx. It equals a to c f of x dx plus c to b. So let me show you this using color. Notice that the upper limit there would be c, and then you'd be starting here from the upper limit and going to some other value. The key thing here, though, is that A is less than C and B is greater than C. So as long as that's the case, it's sort of like you can break it up into parts and do them separately and add them together. That's all it is, and we did do examples like that. But to see it written formally like this only with variables sometimes can be confusing. So I figured that I would show you with numbers first, and then we'd go to these concepts after. And number 4, we practiced a lot as well. If we're looking for the integral a to b of f of x plus or minus g of x, we just can separate them and do them separately. So you can do the integral of just the f of x part first, and you could do the integral of just the g of x part separate. and then add or subtract those together afterwards, and it ends up giving you the same thing. And then this number 5 is just that they're inverse processes. So if you have the integral of the derivative, you're sort of canceling things out, and you would just get the simple basic f of x in the end. So to draw your attention to it, if you're taking the integral of f of x dx, which is the derivative, then you would just get f of x. And in this last one, if you're looking, if we want to look at this example, sorry, not the last one, let's do this example, absolute value x from -2 to 4, if we want to work our way through this, although I didn't ask for it, we could do this. If we go to graph out or sketch out what this graph looks like, it looks like this. And we're looking for -2 up to this value of 4. So it would be like we color this in, we color all of this in. And so we can sort of start to use some of these rules, because we could do these separately. If we're looking for the integral from -2 to 4 of absolute value x dx, then we could split it up to say just this part, so this -2. So I could go from -2 to 0 of -x dx, because do you see that that's the negative portion, the portion to the left? Plus, we can split it up to say we want to look at this portion here as well. So for that, I could say I want it from 0 to 4, because that would be my 0 mark there, of just positive x dx. So you can see that splitting them up, but overall it's going to give you the same end result. And when we go to do that, it would just be us saying -1 over 2x squared when I take the integral of this, or antiderivative, from -2 to 0, plus I do the same thing over here. When I take the integral of this, I'd get 1/2 x squared, and that's going to be from 0 to 4 from this part. So you get to see what I'm saying. We truly do the same thing over and over and over again. It's just a matter of you knowing what to do with it. So then when we work our way through this, here we would just, you can plug it in and do this. I know you all know how to do that. You'd get 2 there, plus when we plug all this in and do this, so the 1/2 4 squared minus 1/2 0 squared, you know that we would just get 8 there. So overall, what we end up getting for the total area ends up being equal to 10. Okay, so yeah, that was sort of quick, fast and quick. I said quack, but anyways, it was a fast run through, but only because it's built on old concepts. Just know that all the stuff we just did is called the fundamental theorem of calculus. So when you get questions asking you to use that, just do the same old thing we've been doing.